Okay, we're starting a really important packet now. The last unit or last couple of pages I did with you were all about your 7th grade constant proportionality type equations and graphs. And remember, the equation was in the form of y equals kx or y equals mx. K and m are both the unit rate or the rate of change. And then the line always went through 0, 0, and the rate of change made the line usually ascend up to the right. Therefore, it's a showing like a price per item and how many items you bought and so on. Okay, moving on to 8th grade linear function. This is packet 1. Okay, I'm going to go page by page, and your goal is to do exactly what I am doing. So if I am writing on the packet, you are as well. I will try to go slow, and I will repeat myself at certain points to emphasize what is important. I'm hoping these little demos won't take more than 15 or 20 minutes, and then you have the homework pages to do on your own. Okay, so the package you have in front of you is Linear Functions, Packet 1, Notes 1 through 7, and the lessons and the homework practices enclosed. Bear with me as I kind of manipulate the pages. First page. First page is an overall overview of what you are now going to learn about. 8th grade is linear equations or linear functions. Function is a fancy word for equation. Once you hit 9th grade and above, you use the word function all the time, and it's introduced in 8th grade. So this is the form of a linear function. The middle one is a quadratic function, and quadratic will always have the x square in it. It's usually this kind of U-shaped figure called a parabola, okay? It could be going this way or it could be going the other way. Sometimes we call it smiling, and if it's flipped over, frowning, all right? And the last one here is called an exponential function. And an exponential function is often talking about growth of like stock market, price increase, the rapid growth of a disease spreading. If you've ever heard it's happening at an exponential rate, that would be this. And it takes off in a very quick way, hence this quick line usually going up fast. The exponent is the x, or the x value in your table of items or numbers, okay? So, brief overview. Linear function, quadratic function, exponential function. We will be graphing and learning all about linear today, okay? I'll expose you to some of the quadratics and some of the exponential, but for now, it's basically linear. On the bottom, we have the definitions of vocabulary. So a function is a relationship that assigns exactly one output, and an output is your y value for each input, and the input is the x. Okay, remember the input is the independent variable. It creates the y, and that's why the y is called the dependent variable. All right, a lot of terminology you will become very familiar with. A relation is a set of ordered pairs that usually form something. And what we're going to be looking at is linear ones. A linear function is a function that forms a straight line when graphed. Nonlinear, hence nonlinear, is not a straight line when graphed. A parabola is the quadratic function from above. It's the U-shaped curve from the quadratic function, and you have an x square. Often this bears on as a multiple choice question. If you see something with an x square in it, it will be parabola or quadratic, okay? Domain, very important to learn this word. Domain is the possible values for the input or the independent variable of the function, which is the x value. Guys, the domain is your x, always. And your range is the possible values for the output, and it's really created based on whatever the input was, okay? The input being put into the function, okay? An input is you put values into the function, which is put into the equation, and you see what comes out, and that would be your output or your dependent variable. In our cases, it's the y value. So domain is the list of x values, and y is the is the range, domain and range. Okay, next page. Work with me as I do this. All right, given the table, plot these values. Is it going to be linear or nonlinear? Well, you can't really tell until we plot them. This is a good practice in reminding you how to do this. I hope your graph is clear. Mine's a little light, so I'm going to have to count. Okay, so -2, 4. So -2 up 4. Right here, put a dot. -1, so I go back to 0. Notice I always start at 0, 0. And I go -1, 1, put a dot. 0, 0 is the origin. Okay, it looks like it's not going to be linear. Over 1, up 1, I'm matching them here. Over 2 and up 4. And I look at that, I have a mirror match. As if the fold line was Y, I could overlap these. If I connect these, I have what I would call a parabola. Okay, this is a parabola. Parabola, it is a quadratic function. Okay, it is not linear. It is not L-I-N, linear. Okay, this is a parabola. It's got a quadratic function. It is not a linear function. This would make a little curve. All right, now another thing you will eventually learn or see is when you see a table of elements, and on the y side here, look what happened. 4, 1, 0, 1, 4. There was a turning point, and the turning point is beautiful at 0, 0, right here, where this function was coming down and then went up. And they mirrored the other side, looking at the y's. Okay? All right, let's go down to the bottom. I will tell you this right now, looking at this equation, it's got an x square in it. Anytime you have an x square in it, it's going to be quadratic, okay, which will probably graph as a parabola, similar to this one. So let's give it a shot. You have to know how to fill in these charts given the equation. So this is the function. The function is y equals x squared plus 2. This is like a little machine. A function is sometimes called a machine. Feed the machine the domain, which is the x values, and determine what it spits out for a y, meaning the range. So domain and range, and then you get the coordinate based on going through this machine. So feed the machine. Watch. Stick with me. -2 squared, so I'm just substituting, plus 2. Now do the math. A -2 squared is positive 4 plus 2 makes 6. So y, in this case, if I fed the machine -2, okay, now remember it's -2 squared, so -2 times -2 is positive 4. Plus this 2 makes 6. So my coordinate is -2, comma 6. Let's do the next one. Put a -1 in the machine. So -1, square it, plus 2. Negative times negative makes positive 1, plus 2 makes 3. So my y value will be 3. So when x is -1, my output is 3. Put a 0 in there. 0 squared is easy. It's 0 plus 2 is just 2. So the point would be 0, comma 2. Put a 1 in there. 1 squared plus 2 makes 3. Put a 3. So here I go, 1, comma 3. Do you notice something? 6, 3, 2, hit a 3. I'm guessing this one's going to be a 6. Since we're in order, it matters that we're in order. We just didn't randomly pick out any old strange numbers. Notice this is a number line starting at -2, -1, 0, 1, 2. Okay? So put a 2 squared plus 2. 2 squared is 4, plus 2 is 6. Hence the term. Okay? Now I'm going to graph these over here. So -2 up 6. -1 up 3. 0, 2. 0, 2 means don't go any place left or right, but go up 2. 1, 3. Over 1, up 1, 2, 3. There's my how I'm turning. And the last one is 2, 6, over to 2 and up to 6. Hence this nice little U again. We connect the dots and put arrows on the M. Again, this is a parabola. It is from a quadratic function because of the x square. All right. Now, let's compare the two graphs. Basically, aren't they very similar? Very similar in size. Its location is just slightly different. And the location is that this is what we call the basic quadratic function. This one was +2. And therefore, it just shifted up 2 units, and this is where it turns. But basically, they're very, very similar. Okay? So the first one is, this would be y equals x squared. All right? And if I had to make a table of values of x and y, and I started at, let's start at -2. If x was -2, -2 squared makes +4. Isn't that what happened here? -2 made +4. Put a -1 here. If x is -1, so -1 squared makes just 1. 0 makes 0. +1, 1 squared is 1. And +2, 2 squared is 4. Hence, it's the exact same table. Okay? So this is the basis of a quadratic, y equals x squared. This one, y equals x squared plus 2, meant it started at 2 and basically did the same design. We good? I'll give you a second to kind of catch up. So the difference between two graphs is one turned at 0, 0, and the other one turned at +2 on the y-axis. Okay, moving on. Okay, let's take a look. This is a question from a state test. You need to understand what's going on in interpreting a graph like this. The graph below shows your speed at different times riding a bicycle uphill, downhill, and on level pavement. All right, let's think about this a minute. Don't get confused. This is not the hill, okay? This is not the hill. This is the speed you're traveling while riding your bicycle. And you happen to be riding up a hill, down a hill, and then flat. So most of us could right away understand the flat speed is right here, is the flat line. That's a steady speed. And the steady speed looks like it's kilometers per hour. Looks like it's you're at like 7 kilometers per hour at the steady speed. Okay? The bottom is from the start per minute. Okay. The question says, for how long were you going uphill? For how long were you going downhill? And for how long were you riding on the level pavement? Okay, so we need to interpret what the lines are. Let's look at how this line is starting at, let's say, 5 kilometers per hour. All right, 5K, kilometers per hour. And it's increasing, right? It got all the way up to 9. So this is getting faster. You with me? So speed is increasing here over 3 seconds time. Somehow you started out doing 5, okay, and got to 9 kilometers per hour within 1, 2, 3 seconds. So tell me what is going on here. Are you going uphill or are you going downhill? Since speed is increasing, you are likely going downhill. So how many seconds were you doing this increase in your speed? 1, 2, 3. So going downhill, I'm going to put a little 3 next to it. Meant 3 seconds. So now we're at 9 and we actually seem to be slowing down. We're slowing down to 7 kilometers per hour. What's the likelihood here? You are probably trying to pedal uphill. So from this second, which is 3, and you went all the way over to 7, is how many seconds? 4 seconds. So 4 seconds going uphill. And then the last interval, it appears you're staying steady at 7 kilometers per hour from here to here, and that's 1, 2, 3 seconds on flat level pavement. So my answer here, A, B, C, or D, I'm looking for 4, 3, and 3. 4, 3, 3, right here, A. Okay, guys, this was definitely a question on a state test. And how many kids thought this was, oh, that's uphill, that's downhill, and that's level? Absolutely wrong. Speed is increasing. You don't increase your speed going uphill when you're on a bike. Okay? It was a trick question. All right, next page. Oops, sorry. Okay. Next one. Let's take a look at this one. Okay, a car traveling at 23 miles per hour accelerates to 46 miles per hour in 5 seconds. So, okay, it maintains that speed for 5 seconds and then slows down for 5 seconds. Which graph demonstrates this car's speed? So I'm looking for to match this story with one of these. Again, another question from one of the state tests. So, clue, start. The car traveling at 23 miles per hour accelerates to 46. So if it's accelerating, it's starting at 23 and accelerates to 46, I need to find where it's starting at 23. First thing. So I look at this graph, this is starting here. So I can eliminate that right away. That's starting, somewhere around 40, 46. This one starts at 0, so I can eliminate him. Now I got to compare these two. This one looks like it's starting at 23. Yeah, that could be it. Oh, so does this. So these two are similar. But the question said it accelerates to 46 miles per hour in 5 seconds. So the first 5 seconds, the speed is increasing. Is it this one or is it this one? Speed increasing. Bingo. Okay, first 5 seconds, it's increasing. Got up to like 46. And then it maintains the speed for 5 seconds. So next 5 seconds stayed at 46. And then it slows down for 5 seconds. So between 10 and 15 seconds, slowing down. Done. Sorry, that's Max. Max!